Okay, so welcome back to our last Chapter 3 video. The last topic we're going to talk about is relative velocity. So this is somewhat similar to what we talked about in an earlier video when we looked at the example of a person walking from the back of a moving train to the front, and do we measure the person's velocity with respect to the train or with respect to the ground outside? So in this particular case, we have a boat traveling across the river. And so it has a certain velocity, but the surface on which it is floating is moving. So relative to the shore, to solid ground, it is moving basically in two ways. It has two velocities. So in this example here, in this diagram, we have the boat that is traveling with respect to the water. So velocity of boat on the water, or with respect to the water. But then we also have the velocity of the water with respect to the shore. Those two velocities will combine to end up causing the boat, if it aims straight across the river, to have a downstream diagonal vector, and that would be the velocity of the boat with respect to the shore. So these two different velocities come together to create a resultant. So if we look at an example problem here, we have a boat that can travel in still water at a velocity of 1.85 meters per second. But this boat captain is smart enough to know that the river current is going to take him downstream. So he wants his velocity to be such that when combined with the velocity of the water with respect to the shore, he will end up going directly across the river, which is, if this is like a ferry boat, for instance, is the shortest, most direct route it wants to take. It wants to get straight to the other side, therefore it needs to aim upstream. And at full out throttle, it's going to be 1.85 meters per second. The question is, what's this angle? How far upstream should the boat aim, so to speak? The velocity of the water with respect to the shore is 1.2 meters per second. So this may seem kind of confusing because we've got multiple velocities going on. The boat is moving, the water is moving. But really, if we just break this down into a simple diagram, the problem becomes pretty easy. So we have the boat traveling at 1.85 meters per second, and it's going in an upstream direction. The velocity of the water is going to bring it back to the left, and that's going to result in a resultant going directly across the stream. This ends up creating a right triangle. And so the side opposite the right angle is the hypotenuse. And if this is the angle we want to determine, this side would be opposite from that. So we've got opposite and hypotenuse. So if we think of SOHCAHTOA, we've got O and we've got H. So that would be O or SO. So it's sine that we want to use. So sine of the angle, sine of theta, is the opposite side, 1.2, divided by the hypotenuse, 1.85. 1.2 divided by 1.85 is 0.649. And to get to get theta all by itself, we get rid of the sine and move it over to the other side by taking the inverse sine. So theta is inverse sine of 0.649, which equals 40.4. And that's it. That's the final answer. The boat captain needs to aim upstream at an angle of 40.4 degrees. Okay, so that finally brings us, there goes the boat. That finally brings us to the end of Chapter 3. I encourage students to use the discussion board to post questions. If you have a question about something, there's a good chance that someone else in the class does as well. And using the discussion board allows those questions and answers to be read by everyone in the class, so it can really be beneficial to everyone involved, posting those questions there. Yeah, as the slide says, that's all, folks, and I'll see you next week with Chapter 4.